So welcome to Baum presentation. My name is Young-Soo Shin, working as Baum CEO. Baum was established in 2016. It is privately held and funded. We have two offices, one in Seoul and the other in Daejeon, Korea. Our executive team includes myself and Junan Lee as CEO and Dongcheol Jung as Chief Business Officer. We have a website and LinkedIn pages as shown here, and we can be contacted through this email. We have a sales channel in a number of regions, including Korea, China, Japan, and Israel. We have a partnership with Verific for their Verilog and the System Verilog partners. The partnership with Synopsys, Cadence, ARM, and the Mentor are for design flow support and for emulator support. We have been covered in a number of medias, mainly in US and Korea. We also have a regular booth at Design Automation Conference. It is no secret now that power is important in electronic devices. More become mobile devices where power consumption and battery lifetime are keys. More circuits are integrated in smaller footprints, which only increases power and thermal density. Devices these days process more and more data, such as multimedia, gaming, AI, and the big data, so they consistently consume power. Let me give you a very brief overview of power analysis. In RTL power analysis, RTL design goes to function simulator to yield RTL FSDB. The analysis takes RTL description and extracts a NAND prototype or rough NAND through internal synthesis. Such a prototype NAND is linked with a particular technology library and becomes a target for the analysis with given RTL FSDB. In gate level power analysis, either pre-NAND or post-NAND is simulated to extract the gate level FSDB. The NAND and FSDB are processed to get the power numbers. In both RTL and the gate level, the analysis can be performed in two different modes. To get average power numbers, FSDB or SAFE is analyzed to get some statistical numbers, such as toggle counts, which are combined with NAND structure for the analysis. To get transient power or power waveform, FSDB for one time window will be processed on the NAND, which is iterated over whole time windows of FSDB. There are a number of limitations in current power analysis solutions in the market. They mainly focus on average power analysis because of runtime, but simple power numbers alone are not informative enough when designers search for some clues for power optimization. What is really important for designers is transient analysis, which, however, is way too slow and so can be limitedly used for very short scenarios. Once power analysis has been performed, there is no way to reuse the analysis result under different scenarios or for different designs. In system-on-chip design, for instance, power analysis of a whole chip should be performed, even though each IPs have been analyzed before. FSDB files, in particular, gate-level FSDB, are very big and take a long simulation time to get. Emulators still rely on simple toggle counts for rough estimate of power, because current power analysis solutions and the emulator cannot be integrated together. Baum solution is based on what we call power model, and so it is completely different from simulation-based solutions in the market. As shown in this figure on the left-hand side, Baum extracts power model from lemlist and a sample FSDB, in which model is trained through gate-level power analysis engine called PowerWater. Once model is created, it is connected to RTL function simulator or emulator for actual analysis with great speedup, about 100 times in case of RTL function simulator, or about 1,000 times in case of an emulator. The key is to extract the power model from gate-level lemlist for higher accuracy, but to perform analysis through RTL simulation with very high speed. This is a simple demo with video decoder. The black is RTL simulation terminal, and the white will show power waveform generated from the model. As you can see, the waveform is generated on the fly for 20 millisecond test scenario, which is very, very long. In this table on the right-hand side, Baum is compared with gate-level and the RTL power analysis solutions. With gate-level analysis as a golden, RTL has inaccuracy of 28%, which is typical, but the error from Baum is less than 5%. The runtime of both gate-level and RTL analysis is around 90 minutes or 100 minutes, but Baum takes only 0.5 minutes, which represents about 200 times speedup. Baum is the only true solution for emulator-based power analysis. This is being used by a few semiconductor companies. Power model is connected to emulator as shown on the right-hand side. Emulator dumps out the small FSDB file that contains signals that power model refers to for actual analysis. Once a power model is created, it can be used over and over. This is very convenient for SoC designs, since power models for IPs can all be integrated and connected to RTL simulator for SoC level power analysis. Model-based approach is also convenient in AI chips. Power model of just one processing element, indicated as PE in this figure, is created, and a number of such models are now connected to RTL simulator for this array architecture of AI chip. IP can be provided together with its power model, which increases IP value. Long test scenarios can be analyzed while transient analysis is performed, which provides a comprehensive power optimization opportunity during RTL design, during sign-up, or even during ion drop analysis. Baum can be deployed in both early and the late design stages. In early stage, whenever RTL is updated, it will be synthesized for pre-analyst. Baum supports both RTL and the gate-level FSDB. So in this early stage, RTL FSDB with pre-analyst may be used to get the power model, which is then followed by actual analysis. Power waveform, together with some optimization feedback, such as OCGR, standing for operational clock gating ratio, which is the percentage of flip-flops that are gated cycle by cycle. Designers usually extract plenty of intuition and information for their next round of RTL update to optimize for power. The whole flow that I mentioned before will then be iterated through batch process. In late stage, post-analyst with gate-level FSDB may be used to create the power model. SPEF may be provided as well for higher accuracy of power model. The figure on the left hand is from one of our customers who designs the GPU. The red here is initial power waveform generated from a Baum. GPU is idle in period 1 and 2, even though power consumptions are different, 20 versus 38. This triggered the designers to look into their design. It turns out that for this design, some memory blocks were not gated in period 2, even though GPU function is correct. This could be named as a power bug. Such bug was removed in updated RTL as confirmed in the new waveform shown below, which also indicates 23% average power reduction. If only average power is checked, as most solutions in the market do, this power bug will go unnoticed. In the figure on the right-hand side, the initial power waveform is shown in red, except for a high peak, which is located at 189 milliwatts. Power consumption here is rather plain. This design has support of dynamic frequency scaling. So they decided to lower the frequency around the peak. So as shown in this green waveform, the computation around the peak is spread out and the peak is much lowered and is located at 104 milliwatts. This is another example indicating that simple average power number doesn't serve for power optimization. And fast extraction of power waveform for long scenarios offered by Baum is important. With this simple presentation, I would like to introduce Baum, which is the best in power analysis solutions. It is very fast because analysis is done with high-level simulators, such as RTL simulator or emulator. We still keep the very high accuracy because power model is extracted from actual design analyst. Power model is portable, so it can be used over and over for different designs and under different test scenarios. IP power models can be integrated, which is ideal power analysis solution for SoC or AI kind of chips. Thank you for your attention for this presentation and for Baum.